Okay, welcome back. So, this is kind of the very last thing we wanted to talk about in the course. It makes sense, right? The today's the last day, so whatever I want to talk about, I kind of have to finish today. So whatever I do talk about is going to be the last thing we're going to talk about. But anyway, this topic that I mentioned yesterday is non-integral methods for autonomous planar systems. Okay, so what is the deal here? Well, um, so consider the following autonomous planar system. So we'll say x prime is f of, eh, hold on, let's rewrite this. Let's rewrite this differently. So let's write this as dx dt is f of xy, and dy dt is g of xy. Okay, so here's our autonomous planar system. Um, and I want to discuss non-integral methods, which is as I talked about yesterday, is basically what we do when we can't find an integral for this, right? So remember the orbit equation was minus g xy dx plus f of xy dy is equal to 0. Now, if this thing has an integral, then we find it by the methods of chapter 1. If we can find an integral, this tells us a ton about what it is that we're looking at, right? So if we can find an integral h of xy for this thing, we are very happy. Okay, because as in the previous example, we're done in the sense that we have basically solved this thing in the sense that we can generate a plot that has all of those trajectories, right? Those trace out what the solutions of the thing look like. Okay. Um, and so we can, if we have the integral in front of us, right, these level sets of this h that is my implicit general solution to the system. And so basically any question that I want to ask about behavior of solutions of the system, I can answer from this integral. So the integral is us solving this differential equation, okay, or this system, this autonomous planar system. And so this is obviously nice, and we're very happy if we can do this. Now, we know that it happens that sometimes we can't, so what do we do? Do if no such h exists? Okay. All right, we have to rely on non-integral methods. Okay. So, what are these non-integral methods? Well, let me get some more paper. Okay. So, these non-integral methods, the primary tool that we're going to use to say something about the behavior of solutions to these systems is linearization near stationary solutions. Okay, so the main idea is to consider linearization about stationary solutions or stationary points. Okay. So what is this? Well, the idea here is the following. From Calc 3, we can linearize f and g, which means we use their multivariate Taylor expansions to approximate these things near a point. So f and g, we can use approximation of f, xy, and g of xy about the point, say, x naught, y naught. Okay. Okay, so if we do this, this leads to f of xy being f of x naught, y naught plus first order terms in the derivative. So this would be x minus x naught times the x partial of f evaluated at x naught, y naught plus y minus y naught times the y partial of f evaluated at x naught, y naught plus higher order terms. Okay, so higher order terms come next. I can do the same thing for g. So I have my 0th order term, which is just g with that thing plugged in, plus x minus x naught times the x partial of g evaluated at x naught, y naught plus y minus y naught times the y partial of g at x naught, y naught. Okay. Okay. So then if we say that the higher order terms, let's just drop the higher order terms. This is a first order approximation or a linear approximation of f and g. Okay. So if I drop these, so if I just ignore those, these give a linear approximation of f of xy and g of xy. Okay, now remember the intuition here coming from calculus, right? So this was the idea of approximating. I mean, in the 1D case, this is the idea of approximating the graph of a function by its tangent lines, right? So we could think of the derivative as being a sort of linearizing or linearization of the function in question. Basically, the idea is that you can replace info about the function with info from its derivative, which linearizes the function, right? So think, like I said, in the 1D case, you have that thing. You can replace this with tangent data at a few points. So if I right, if I draw in all the tangent lines, even if I went back and erased or deleted my original function, you could still tell what the thing looked like, and now you've replaced it with this piecewise linear thing. So this was, you know, a calculus version of what we call the linearization of a function. So the derivative is a linearizing thing. Okay. So then from this fact, well, if x naught, y naught is a stationary solution, then f of x naught, y naught is 0, and g of x naught, y naught is 0, right? Remember, the system in question looks like this. So a stationary solution is a point xy such that f and g are both 0, right? So that these derivatives are both 0. Okay. Well, but if these two things are both 0, then these first two terms are going to go away at stationary solutions. And so what I get here is that f of xy near a stationary solution is approximately x minus x naught times the x partial of f at x naught y naught plus y minus y naught times the the y partial of f at x naught y naught, and g of xy is approximately x minus x naught times the x partial of g at x naught y naught plus y minus y naught times the y partial of g at x naught y naught. Okay. So this is the linear approximation of f and g that we get near a stationary point. Okay, so near a stationary point or stationary solution, this is the linear approximation for f and g I get. So if I shift then, right, so this is shifted by x naught, y naught. If I consider a shifted system where I've just added in each component x naught and y naught, what do I get? This tells me that I have the following fact, that I have this approximate solution, ddt of like x tilde y tilde, where this is the shifted thing here. This is the matrix that is the x partial of f at x naught y naught, the y partial of f at x naught y naught, the x partial of g at x naught y naught, and the y partial of g at x naught y naught times x tilde y tilde. Okay, so this leads directly to this. Okay. This is called the linearization. This is the linearization of the system star, which is this one. So this is the linearization of this system about the stationary point x naught, y naught. Okay. This coefficient matrix is called the Jacobian, okay, of the system. So this matrix, I'll rewrite it again. So it's this thing with f and g plugged in. Is called the Jacobian of that system. This is the Jacobian matrix. Okay. All right. So what is the idea? This is the important thing. Use the linearization near stationary points to get info about local behavior of trajectories. We're not going to be able to deduce anything about global behavior necessarily, but local behavior, and what we mean by that is near the stationary points. Near the stationary points, we're going to be able to see what happens. Okay. All right. So how do we do this? Let's use an example. Our favorite example from these couple sections. So let's compute the linearization of the system x prime equals y, y prime equals 4x minus x cubed, okay, about each of its stationary points. Then deduce info about its phase plane portrait. Okay. So first of all, what are the stationary points? So recall, right, we have already computed stationary points to this thing. We previously found that this thing has stationary points 0, 0, minus 2, 0, and 2, 0 are the stationary points. Remember how we found this. So you could either find these as critical points of the integral. We know that this thing actually has an integral, so we don't need to do these non-integral methods, but we're going to do them anyway because we already know what the answer is, so that we can actually check that what we get makes sense, right? Okay. So we previously found that 0, 0, minus 2, 0, and 2, 0 are the stationary points, and we found that just by setting these things equal to 0, right? So setting f and g equal to 0 here. Okay. So now I need to compute the Jacobian matrix near each of these things, right? So the textbook writes it as writing this as a vector f of xy. This is f of xy, g of xy. So the vector writes the Jacobian as del f bar. So del f bar is the Jacobian. You don't have to use this notation. You can just write it out. It doesn't matter to me. Okay, so what is the Jacobian? This is the x partial of f, the y partial of f, and the x partial of g, and the y partial of g. There's my Jacobian. So let's compute this real quick. What is the x partial of f here? 0. What is the y partial of f? 1. What is the x partial of g? Well, it's 4 minus x squared, right? Or 4 minus 3x squared, sorry. And what's the y partial of g? 0. So there it is. Okay, there's my Jacobian. All right. So now I have to check what this Jacobian is at each of these things. Okay, at 0, 0, my Jacobian is the matrix 0, 1, 4, 0. This is my linearization matrix. Okay, this is the same at plus and minus 2, 0, so at plus or minus 2, 0, my Jacobian is 0, 1. This would be 4 minus 3 times, whether it's plus or minus 2, this would be 3 times 4, so this is 4 minus 12, or this is minus 8. 0. Oh, sorry, I'm slightly off the page. Okay. And so this is my linearization matrix. Okay. All right. So now, what do I do? Well, what I do is I basically do my classification of phase plane portrait stuff to figure out what this means, okay, for my system. So now I do classification of phase plane portrait stuff. For each linearized system. What do I mean by that? Well, I have at 0, 0, my Jacobian matrix is this thing, right? So at 0, 0, my Jacobian matrix, which I'll call A now, is 0, 1, 4, 0. Okay. What is the characteristic polynomial of this thing? Well, this is z squared minus the trace, which is 0, minus the, or plus the determinant, which is 0 minus 4. So this is z squared minus 4. So this is z plus 2, z minus 2. So this has eigenvalues. Lambda equals plus or minus 2. Okay. If I were to find associated eigenpairs for this thing, right, how would I do that? So if I look at a plus 2i, what is this? This is going to be 2, 1, 4, 2. If I look at a minus 2i, this is going to be minus 2, 1, 4, minus 2. So then this thing has eigenpairs. If I'm using minus 2 first, then any non-zero column of a minus 2 is going to give me an eigenvector associated with this eigenvalue. So I'm just going to pick the second one. So this is 1 minus 2 here. And my other eigenpair would be 2, 1, 2. Okay. So these are 2, 1, 2. So then what does this give me when I have eigenpairs for a coefficient matrix? Both real eigenvalues, one is negative, one is positive. What does this give me? Well, this gives me a saddle. So along the eigensolution or line solution associated to this thing, I'm going towards the origin, right? And then associated to this thing, I'm going away from the origin, right? Like this. Okay. So we'll draw that in the picture here in a second. Okay. All right. At plus or minus 2, 0, my linearized matrix, this Jacobian, is 0, 1, minus 8, 0. Its characteristic polynomial is z squared minus trace, which is 0 here. The determinant is 0 minus minus 8, so this is z squared plus 8. So this has roots, we'll call them lambda is equal to plus or minus square root of 8 times I. So these are complex conjugate roots. Okay. Well, these are complex conjugate roots, and notice this is mu plus I plus or minus I nu. Right, so nu here is root 8, and mu is 0. So mu is 0. Notice also this entry, A21, is minus 8, which is negative. Complex roots, the real part's 0. A21 is negative. What does that indicate? Okay, this is a clockwise center. So clockwise center near plus minus 2, 0. Okay. So what does my picture look like? I'm going to draw in subtle axes, because of course, like I said, I don't want the axes to be confused with trajectories here. I'm going to draw in some axes so I can plot these things. Okay, so I have 3 stationary points, right? So 3 stationary points, 0, 0, minus 2, 0, and 2, 0. There we go. Okay, there they are. Near 0, 0, my linearized matrix, this Jacobian, is 0, 1, 4, 0. Has eigenvalues plus or minus 2. The real opposite sign, that leads to a saddle. Okay. Now you say, do I have to find eigenpairs? Technically not. If all you care about is whether this is a saddle or not. This is just if you're doing any more with this, if you wanted more info about exactly how these line solutions look, for instance. So this is a saddle. So what I'm going to do is near this I have a saddle. So I have line solutions that look like this, where along the vector determined by 1, 2, which would be this vector, I have positive motion. So right, this is positive, so it's moving away from the origin. Along the other one, I have motion toward the origin. So that's what's going on. Any other trajectories nearby look something like this. It would look something like that. Okay. What about near these points? Well, we just saw that at plus or minus 2, 0, my matrix is 0, 1, minus 8, 0. This has roots plus or minus root 8 I. This has real part 0. The A21 entry in the coefficient matrix is minus 8, so it's negative. So this leads me, by that classification of face plane portraits, this leads me to the case where I have clockwise centers near both of these. And so near these points, I have these centers, and they are clockwise. Right? And maybe here's another one. Okay, so that's what we have. Now, what do these non-integral methods allow us to say? Basically exactly what we wrote down here. We know that near these stationary points, this phase plane portrait has to look like this. But it doesn't really allow us to say what's going on out here. Okay? And the reason it doesn't is because this whole analysis, this whole approximation was only valid near the stationary points. So when you're not near the stationary points, this is not valid, so we just don't know what to say out here. Okay, but we can at least get this picture. Now, of course, compare this, right, with the actual solution, right? It turns out this thing is integrable, right? This thing has an integral. But this system has an integral from last time. So this is what we did last time. So we can just check to see if this matches what we found before. Okay. Well, yeah, right? It matches. So notice that here we had the complete picture. We know that this is exactly what this thing looks like. In this case, we don't know exactly the complete picture, right? We only get a picture nearby here. Okay. And yet you see that, oh, like on the bits we actually know, these match up perfectly, right? So this is definitely a good approximation here. This is a good way of getting some info about the behavior of trajectories because we see how it matches up. For this case where we actually had an integral, so we can just check that these things match up the way they're supposed to, right? So that's the idea. Okay. All right. Yeah, let's do another one. So let's do let's do one more here. So first of all, let me pick one of the systems that did not have an integral. It'll kind of be the crowning thing that we do. Okay. So here's an example. Compute the coefficient matrix of the linearization about each stationary point of the system. X prime is equal to y minus x times x minus 1, and y prime is equal to 3 plus 2x minus x squared times y. So, and I'll say, and use phase plane portrait classification to get info about trajectories near each stationary point. And we do this by applying that phase plane portrait classification to these linearized systems, these approximated systems near each stationary point. Okay. All right, so we have already seen that this actually, well, I didn't prove that it has no integral, but I just told you all that it has no integral, so you can just trust me. This thing has no integral, so integral methods are off the table for this thing anyway, so we're not going to have anything to compare this with. If we wanted to compare this with something, we would need to come up with like a numerical solution, right? So we would use numerical methods to give us an approximate solution. We could generate a complete plot numerically, right? But as far as finding an integral, actually analytically solving this, we're not going to be able to do it. Okay, so that's fine. We have previously found stationary points, so from before, stationary points of this system are -1, -1. Because of this, y is, I get y is equal to x for these two. So I get -1, -1, 0, 0, 1, 0, and 3, 3. So those are my stationary points. Let's compute the Jacobian, right? So Jacobian, which is x partial of f, y partial of f, x partial of g, y partial of g. What is this? So here's f of xy, here's g of xy. All right, so I'm going to have to, really use my multivariate calculus skills. Let's actually expand these things, so make this a little easier to. So expanding them is not what you want to do to find the stationary points. So please don't do this expanding first, right? You want them in factored form to find the stationary points, because setting things equal to 0 is very nice if you have it written as a product of a bunch of things. So definitely want to leave it factored like this when you're finding stationary points. But for finding x and y partials of these things, it's better that these be expanded into like polynomial things. So what is this? This is like xy minus x squared plus or minus y, right? Plus x. So that's what I get for f, written like that. And what I get for g is 3y plus 2xy minus x squared y. Okay. So now this makes computing these partials easier. So then what's the x partial of f? This would be y minus 2x plus 1. Okay, that's in the first lot. The y partial of f is going to be x minus 1. That's the y partial of this thing. The x partial of g is going to be 2y minus 2xy. And the y partial of g is going to be 3 plus 2x minus x squared. So there's my Jacobian matrix. So then I need to actually write out the Jacobian matrix here for every single one of these stationary points. So I'm going to get 4 different matrices. Let me put that kind of at the top here. Okay, so there we go. So there's my Jacobian. So then let's do at minus 1, minus 1. Jacobian is what? I'm plugging in minus 1, minus 1 here. So I will get 2, minus 2, minus 4, 0. Okay. So that's what I get. At 0, 0, what is my Jacobian matrix? I get 1, minus 1, 0, 3. Okay. At 1, 0, my matrix A is minus 1, so this would be minus 1, because that's 0, so this would be minus 1, 0, 0, 4. And then at 3, 3, this matrix is this would be 3 minus 6 plus 1, so that's minus 2. 2. 2 times 3 minus 2 times 3 times 3. It's minus 12. And 0 is the last one. Okay. So there are my matrices. Now, I have to repeat this. I have to repeat this analysis for my solutions here. So let's see. First of all, what do I? So first question, what do I do for each of these? Well, let's just consider them matrix by matrix here. So for this first one, right, what's my characteristic polynomial? So characteristic polynomial is z squared minus the trace of z, which is 2, so that's minus 2, z plus determinant, which is 0 minus 8, so this is minus 8. And of course that factors as z plus 2, z minus 4. Okay, so it has eigenvalues lambda, which is minus 2 and 4. So this is a saddle. Okay. All right, so I already know that this is a saddle, and I can immediately find eigenpairs if I really want to tell me exactly how this works. So eigenpairs, I'm just going to go ahead and write them. So this thing has eigenpairs. So minus 2, 1, 2, which you can find, and 4, 1, 1, or 1 minus 1. So this just tells me which of those line solutions is approaching the stationary point and which one's going away from it. Okay. All right. So let's do the next one, 0, 0. This is an upper triangular matrix, so I can just read off the eigenvalues. So eigenvalues, so this is everything I did for the first matrix. Here, eigenvalues are lambda equals 1 and 3. Okay. So these are both repelling, right? These are moving away from that stationary point. So then this is a nodal source is what I get. Okay, I can look at eigenpairs and tell exactly, what this thing looks like. So eigenpairs in this case, I have 1 and 1, 0, and 3 and 1 minus 2. Okay. All right. So what about the next one? What about this one? So this is a diagonal matrix or upper triangular matrix, however you want to see it. So this has eigenvalues lambda equals -1 and 4. So real eigenvalues opposite sign. So again, saddle. Okay. Okay. I could find the eigenpairs if I really wanted to, but I'm not going to. All right. And at 3, 3, what do I get? Well, here, what's my characteristic polynomial? So this is z squared minus trace, so that's minus minus 2, so that's plus 2z, plus determinant, which is 0 minus minus 24, so this is plus 24. I can rewrite this as, if you like, z plus 1 squared plus 23. So eigenvalues are lambda equals -1 plus or minus root 23i. Okay. So mu here is -1, which is negative. And a21 is -12, which is negative. So this is a spiral sink. Okay, and it is clockwise. So this is a clockwise spiral sink. Again, look at your list. Look at your classification of phase plane portrait list, right? So eigenvalues are complex. The real part is -1, which is negative. So that tells you it's a sink and that it's a spiral sink. The sign of A21, this entry in the coefficient matrix being negative, that's what tells you that this is clockwise. Okay. Now from all of this info, I want to piece together what this thing looks like. Okay, so where are my stationary solutions? So my stationary solutions are, actually I need to draw in axes very lightly. So the axes are not trajectories, right? But I want you to tell where things are on this picture. So there's my axes. What are my stationary points? Well, -1, 0, 0, 1, 0, and 3, 3. Okay. So 0, 0 is here. And 1, 0 is here. Okay, and -1, 1 is here. And 3, 3 is like up here. Okay, so each of these are stationary solutions, meaning that if your trajectory begins at any of these points, it stays there forever, right? Okay, now there are actually semi-stationary solutions here, which look like what? So what do the semi-stationary solutions look like? So first of all, let's maybe before I add in semi-stationary solutions, I'm gonna see what it is I'm doing at each of these. So I have a saddle at -1, -1. Okay, so then what does this saddle look like? Well, at -1, -1, I have a saddle. Here's my eigenpairs. So locally, right, I have solutions. I have line solutions coming out of this point. So I have these line solutions. Okay. So there's my line solutions. It's going, so for the line solution for 1, 2, it's going towards. So this is going towards. And for 1, -1, it's going away from. So other trajectories nearby here look like they're doing this. Okay. All right. So that's what this saddle looks like. Okay. At 0, 0, I have a nodal source. So what does that look like? Well, I need to, before I can really finish this picture, okay, or maybe kind of piece together this picture entirely. Well, I'll go ahead and do this. So at 0, 0, okay, so at 0, 0, what do I get? This nodal source would be, so both of these line solutions emanating from this point, I'm going to have motion away from it because it's a source, right? These eigenvalues are both positive. Okay. And so what do I have? I have one of these things is, so this eigenpair here indicates that one of these line solutions lines up with the axis. Right, so one of them is horizontal. Okay, and the other one is not, 1, -2, so it looks something like this. Is my other line solution. I have motion away along both of these. And of course, since it's a nodal source, right, other trajectories nearby look something like this, so that they're matching the direction here, right? And something like this, or maybe this actually turns more like this. Yeah, maybe this turns, something like this. Okay. All right. What about at 1, 0? At 1, 0, I have another saddle. Okay, and it turns out that my line solutions here are actually going to indicate my semi-stationary solutions at this point. So here I have the eigenpairs I get, these line solutions, are going to be exactly vertical and horizontal. Okay, so it turns out I can actually connect this, but I'm going to say why I can do this. Normally I can't do this. I have a totally local picture near these stationary points, but the reason why I can actually connect this comes later when I talk about the stationary solutions. So here, this is the picture I get for the vertical one that is associated to the positive eigenvalue. So that's motion away. And the negative one, or the horizontal one, is associated to the minus eigenvalue, so that's motion towards. Notice that agrees with the motion out from this one. Okay. All right, and then of course nearby trajectories, right, match this picture. Okay. And then lastly, this point, this is a clockwise spiral, so I have no line solutions. I just have a clockwise spiral around this thing, right? This is some kind of coming in like this and coming in like this. This is my spiral out here. Okay. Now, recall we found semi-stationary solutions for this along the following vertical and horizontal lines. So we did this 2 lectures ago. So the semi-stationary solutions actually are along this vertical line and this horizontal line, which is why I could connect these. So these are stationary solutions. Oh, so no, sorry. This is moving towards. This is moving in the that arrow's in the wrong direction. This is moving away. Okay. All right. So this is the picture I get, and this is how I can tell that this thing, wherever it goes, it's not going to cross the semi-stationary solution line. Okay. All right. And so what's most important, of course, is ignore the semi-stationary lines for a second. Just look at the behavior near each of these points. Right? This is pretty complicated behavior for this system. Right? Notice this is stuff that couldn't happen for the integral system. Getting spirals and stuff couldn't really happen. So the question is, does this match up? Well, in order to see that this matches up, you need to actually generate this thing. And you could generate this thing with numerical methods. So to check that this is indeed an accurate portrayal of behavior for solutions to this system, I need to numerically integrate by like Runge-Kutta or something like that. So we didn't really talk about those methods at all, but applying numerical method here to generate a plot like this. You can see this at the bottom of page 12. So this is page 12 in chapter 3, section 9. If you want to see the end result of this and actually what this thing looks like. But it turns out that yes, the behavior of the system is indeed something like this. But notice, this system had no integral, and yet near these stationary points we can still get a very accurate picture of what's going on. Okay. All right, so that is that. that's pretty much does it for as far as the course material goes. So you've now seen all there is to see from this course material. We have covered in chronological order, more or less. We've covered every single section. There were a few sections that are typically optional that don't get covered. So, 3.10 we didn't get to, and typically it's not something that is covered in a normal 246 class. So, so we have finished all the material. And all that's left then is, for you to finish the assignments on your plate and the final exam, which I'm going to post here in a little bit. So I'll post it within like 30 minutes or so of this class session ending. So that is that. It's been a fun semester. Let me know if you had any. Let me know if you had any questions about anything over this weekend. I'll be pretty vigilant with email, so I'll be waiting, for any questions you might have, any last-minute questions about any of the assignments. You can ask me, and I will try to respond as quickly as I can. So anyway, so that's pretty much that. I think I told someone that I would show off the cat, so I might do that for a couple minutes, and I'll hang out here if you have any more lingering questions. But otherwise, thanks for the semester, and I'll hopefully see you all again in the future. Okay, everybody, that's it. That's all. I ran out of cats to show. So anyway, that's it for the semester. I'll, like I said, I'll be on email if you have questions. I'll send out an announcement the second that that I upload your final exam, and then you have until Sunday night to do it. It's short enough that you can. I mean, it'll take you a couple hours to do, but it's short enough that you'll be able to finish it today. So this is not me extending the semester or whatever. I'm just being nice and giving you a couple extra days to do it. But you can definitely finish it today, this evening, no problem. But anyway, that is all. So I will see you all later.